Permanent magnet synchronous machine. The permanent magnet synchronous machine has balanced three-phase sinusoidal distribution of air gap flux and sinusoidal distribution of armature winding. So alternating supply is given. The three-phase induced back EMF also is sinusoidal as given in the following equations for phase A, phase B and phase C. That is EA is equal to AM sin omega t. AB will be lagging by 120 degrees and AC will be lagging by 240 degrees. So here there will be permanent magnets and here there is a field winding. Here is the stator winding. Now we will see the permanent magnet synchronous machine structure. Now replacing the field winding of the wound rotor synchronous machine with permanent magnet poles, permanent magnet synchronous machine is generated. Similar to the conventional synchronous machine, the stator has three-phase distributed armature winding in the stator. The armature winding is fed with three-phase sinusoidal supply, that is current. Then a synchronously rotating sinusoidal air gap flux is created. The permanent magnet rotor with the same number of poles as the rotating air gap flux always rotates in synchronism, which depends on the applied frequency. So the rotor is also rotating with the speed of the revolving magnetic field or rotating air gap flux. Now, on the basis of the placement of permanent magnets in the rotor, the permanent magnet synchronous machine is classified in further categories. Here, we will study some selected categories of permanent magnet synchronous machine based on the placement of permanent magnets on the rotor. The first is surface mounted type permanent magnet synchronous machine, surface inset type, interior radial type, and interior circumferential topology of permanent magnet synchronous machine. The surface mounted topology, here you can see the surface mounted topology. The stator winding is the sinusoidal distributed winding, three-phase winding. And on the rotor, this is the rotor, there are magnets. Now we can see the magnets are mounted on the surface. And these permanent magnets are simply glued on the rotor surface using epoxy adhesive and offering the advantage of simplicity of manufacture. So the manufacturing is very simple, just to place the magnets. Since the permeability of permanent magnets is near to that of the air gap, the effective air gap is the sum of the actual air gap length and the radial thickness of the permanent magnet. So air gap will be the thickness of the magnet and the air gap thickness. So total air gap will be addition of these two. The corresponding armature reaction field is small and stator winding inductance is also low. Since the d-axis and q-axis stator winding inductances are nearly the same, the reluctance torque is 0. So whenever there is difference in the d-axis and q-axis inductances, the reluctant torque is produced. But here the d-axis is the axis from this magnet and the q-axis is in between these two magnets. So quadrature axis. Now the inductances are nearly same and reluctance torque is not contributing. In addition, there is a possibility that the permanent magnets may fly apart during the high-speed operation. So the surface mounted is though simple, there is a possibility of dislodging the magnets when there is a high-speed operation of the motor. Next topology is the surface inset topology. Now, earlier the magnets were mounted on the surface and simply they were glued. Here the magnets are inside this rotor body, rotor surface. It is embedded. Thus, the quadrature axis reactance becomes higher than the direct axis inductance. Now, if you see here, this is the quadrature axis. There is a q axis, and this is the direct axis, d axis. So similarly, all the magnet will have d and q axis here. So q axis inductance is higher, quadrature axis inductance is higher, and the d axis inductance is lower, producing additional reluctance torque. So reluctance torque can be observed here because of this difference in the inductances or net inductance. In addition, the permanent magnets are inset into the rotor and it offers better mechanical integrity than the earlier type, that is surface mounted, and it will withstand the centrifugal force at high speed operation and no possibility of dislodging the magnets from the surface of the rotor. Third type is interior radial topology. In the interior radial topology, the permanent magnets are readily magnetized and buried inside the rotor. You can see the magnets are now very much buried inside this rotor portion. Compared with surface inset, this topology enables permanent magnet well protected from flying apart, thus further improving the mechanical integrity for high-speed operation. As now they are sufficiently buried, the mechanical strength is very good and magnets will not dislodge when there is a high speed. Also, its DQ saliency, additional reluctant torque is also generated. So if we see, this is the quadrature axis and this is the direct axis. So there is difference into the inductance and reluctance torque is generated, and that will also support for the net torque. Differing from the surface inset or as compared to surface inset, this interior radial topology adopts linear permanent magnets that are easier for insertion and they are easily machinable. So we can see the radial topology, the magnets can be easily inserted here. Now the flux is basically in the, if this is the radius, so flux is flowing in the radial direction. You can see here it is flowing into the radial direction, hence it is a interior radial topology. The next type is interior circumferential topology. Here the permanent magnets are circumferentially magnetized and buried inside the rotor. It takes the definite advantage that the air gap flux density can be higher than the permanent magnet remanence, so called the flux focusing or flux concentration. In addition, it holds the merits of good mechanical integrity and additional reluctance torque. So there is also production of the reluctance torque. If you see the D axis and Q axis inductances for this. However, because of significant flux leakage at the inner ends of permanent magnets, a non-magnetic shaft or collar is generally required, which may degrade the torsional stiffness of the rotor shaft. So flux leakage is there and it can link to this shaft and causing the stiffness of the rotor shaft. Examples of permanent magnet brushless motor drives in electric vehicles. The Nissan Leaf stands for a leading, environmentally friendly, affordable, fairly car. It is a hatchback EV introduced by Nissan in 2010. It has the largest market share of worldwide EV sold since 2010. Using its onboard 24 kilowatt-hour lithium-ion battery, it offers driving range of 135 km per charge based on US Environmental Protection Agency EPA profile. The corresponding propulsion system adopts 80 kilowatt and 254 Newton meter front axle permanent magnet synchronous motor drive. With a single speed transmission, it can offer a top speed of over 150 km per hour. Daimler AG plans to mass produce it with availability in major markets worldwide. It features a 55 kilowatt permanent magnet BLDC motor drive, which can offer top speed of 120 km per hour. On the basis of lithium-ion battery pack, 17.6 kilowatt hour, it can run 150 km per charge is the range. With the torque of 130 Newton meter, it can accelerate from 0 to 100 km per hour in 11.5 seconds, which is essentially at par with that of the conventional smart auto. Here we can see Nissan Leaf and the smart auto ED that is using the PM brushless motor drives in their applications.